All right, moving right along. Next is exploratory factor analysis. So what I would do, first things first, I would go back to the data set and save it. We've made several minor changes here and there. I'm going to go ahead and save this as, and I'm going to save it as trimmed and no missing. Let's see, no missing. There we go, save. So now all of our changes are recorded, and if we make a mistake somewhere, we're good to go. And I'm going to go ahead and reorder these variables. Look, we have these guys in the end here because we imputed them. We replaced the missing values. I'm going to resort this column, sort ascending. It's going to say, are you sure you want to do this? The answer is yes. But do you want to save it as a different thing? No. Okay, we're in order now. I'm just going to put age, ID, gender, frequency, experience, all at the bottom again. Okay, there we go. The next thing to do is a factor analysis. I'm excited. I like factor analyses. So, analyze, dimension reduction, factor analysis. What are we going to stick in there? We're going to start with everything. Throw it all in there. All the reflective latent measures. This is critical to bear in mind. You must have reflective, not formative, reflective latent, meaning multi-indicator measures. If you have formative measures, don't include them in the EFA. If you have categorical variables like gender, don't include them in the EFA. If you have demographics that are clearly not part of a reflective latent construct, don't include them in the EFA or CFA. They don't belong in a reflective measurement model. You're only going to include reflective latent factors. Hope that was clear enough. Cool. Throw this in here. If you're not sure what reflective versus formative means, please refer to my YouTube video called Formative versus Reflective Measures in a Factor Analysis. I think it's called that, something like that. Okay, throw these all over. Descriptives, I've done this many times before. Reproduced, KMO, continue, extraction. I like to use maximum likelihood. Why? Well, that's the same algorithm that Amos is going to use when we do the confirmatory factor analysis. I like to do it based on eigenvalues instead of a fixed number of factors, at least initially, just to see what it's going to give me. How many iterations do we want to allow? 25 is fine. Continue. Rotation, I like to use Promax. It's less forgiving, but we might have to switch if we have issues. Continue. Nothing in scores, although just FYI, if you wanted to save each of the factors as a variable, these are called factor scores, then you can click here and save variables, and that'll give you however many factors you came up with in your pattern matrix. It'll create that many more new variables to represent each of those factors in your data set. I'm not going to check that. Okay, cancel. In the options, I'm going to suppress small coefficients at 0.3 because I'm really not interested in loadings less than 0.5, and we need them to be at least 0.2 difference. I've talked about this in other videos. I'm not going to go into depth here. Okay, this is more of a procedural video anyway. We want to look at KMO. KMO looks good, 935. You want this above 0.7, ideally above 0.9. You want the sig value to be significant. This is all part of adequacy. We're going to talk about adequacy, validity, convergent, discriminant, and reliability. Okay, back here. We look at the extraction column, and we want to see if there's anything less than about 0.3. We're at 0.3 on decision quality 8. Borderline, looking pretty good. Okay, moving on. And we have total variance explained. We want to look at this cumulative column. It came up with 6 factors. How many were we expecting? Well, if we go back to our model, we were expecting 1, 2, 3, 4, 5, 6. It came up with exactly what we wanted. This rarely happens, so I'm kind of surprised. And this doesn't provide us an opportunity to do mitigation strategies. So maybe see my other videos for mitigation strategies. Okay, it explains 64.5% of the variance in the model. That's good. We want more than 60%. At a minimum, we want more than 50%, but again, above 60% is ideal. Skip the factor matrix, skip the goodness of fit, go down to the reproduced. We want a number here less than about 5%. We're looking pretty good. And pattern matrix is looking stellar-ish. Ooh, actually, we do have some issues. We have a few issues. This is fun. I don't like it when it just works. So, let's do this one at a time. Atypical use looks fabulous. There are no cross-loadings anywhere. All of the items loaded onto a single factor, factor 5. Decision quality, not so fabulous. Still good, but not fabulous. Look, we have a 0.407, that's fairly low. We also have these two other items from information acquisition that loaded with all the decision quality items. That's a problem. We'll have to resolve that separately. Information acquisition loaded onto its own factor, but look at those loadings. They're awful. So I'm not sure what to do about that. We'll have to address that next. Joy looks joyful. No problems there whatsoever. Playfulness looks incredible. And usefulness looks incredible as well. So the only real problem is this discriminant validity issue between decision quality and information acquisition, which my guess is causing the convergent validity issue with information acquisition. So what would you do here? I would actually just run another factor analysis, but get rid of everything except decision quality and information acquisition. There we go. And just run it again with just those two sets of items. And looking good, looking good. Really what I want to do is go down to the pattern matrix. Good, it did come up with two factors. That's what we wanted. But you can see there are some issues. Decision quality 6 is loading almost equally on both sides. That is the first one I would delete. So let's do that. Factor analysis again. Decision quality 6, sayonara. Okay, run it again. Jump down to the pattern matrix. Decision quality 1, loading on both sides. Hey, look at these loadings though. Ooh, those are looking better. Okay, this one, no good. Decision quality 1. And you may say, hey James, wait, what is this? It's above 1. It was last time too. We're going to ignore this is called a Haywood case. We're going to ignore this Haywood case until we've resolved other issues, because it'll probably just resolve itself. So, decision quality 1, you are gone. Kicked off the island. There we go. Jump down to the pattern matrix. Looking better, but look at this. Decision quality 8, not really contributing very well. I'm going to drop decision quality 8. And pattern matrix, much better. This is borderline, we might keep it. This is also borderline, we might keep it. What I'm going to do at this point is I'm going to recreate the larger pattern matrix and see if everything's resolved. If not, we can see where we'll go. Probably decision quality 7 and info acquisition 5 will be the next to be eliminated. So back to the full factor analysis. We're going to throw everything in there except decision quality 1, 6, and 8. Yep. Run it again. And I am just going to do a few cursory things. I'm going to jump down here. It looks like we still have 6 factors. Excellent. Good variance explained, actually better than before. And we have only 3% non-redundant residuals this time. And here's the pattern matrix. And it already looks better. Okay, decision quality. That looks really good. Information acquisition. Also very good. Wow, actually I wasn't expecting it to be that good. And everything else looks just as good as before. What I might do is drop information acquisition 5. It is still fairly low, and you can see these loadings here, 0.7, 0.7, 0.7, 6, and 4. These aren't going to average out to above 0.7, which is a problem. If I want to verify this, what I might do is do reliability analysis. Analyze, scale, reliability, and just stick in those information acquisition items. Here we go, pull it over, and then go to statistics and do a scale of item deleted, continue, and OK. And what this is going to tell us is if dropping that item will actually do us any good. So it was, let me go back up to here to the pattern matrix. It was information acquisition 5. Now if I go down to the reliability analysis, click here. If you look at this last column, it says what our Cronbach's alpha would be if we deleted each of these items. The current Cronbach's alpha is 0.842. But if we deleted information acquisition 5, it would go up to 0.846. This isn't a big difference. And so if I was struggling, if I wanted to keep all these items, I'm fully justified in keeping all these items, even though that is a low loading. Most likely scenario is it will bump up a little bit during the confirmatory factor analysis in AMOS, so I can keep it. If I really don't care, and these are scales I made up myself, and I had the liberty to do so, then I might just drop information acquisition 5, which is what I am going to do at this point. So I'm going to run this one more time, drop InfoAc 5, watch what happens to see if it makes big differences. That's an uptick, which is good. 3% is the same. Ooh, okay, so it actually caused some problems. It threw in a new loading here above 0.3. What happened is information acquisition 5 helped distinguish us from decision quality, whereas now we're having a hard time distinguishing ourselves. So I'm going to retain information acquisition 5, even though this is a greater than a 0.2 difference. It did bring up that discriminant sort of cross-loading issue. So my final pattern matrix is actually going to be the one with information acquisition 5 still in it. Here we go, run it. What do I report? I report the KMO, say it's awesome. I report the SIG, say it's awesome. These are all under adequacy. Under communalities, this is another adequacy measure. I look at the extraction column and I say all of my communalities were above 0.3. Looks like they are. The lowest one is this one, 0.397. And then I'd say the 6-factor model explained 66.3% of the variance, which is good. And then I'd say we had less than 3% non-redundant residuals, which is great. And here's the pattern matrix. And I'd say as evidence of convergent validity, we have all the loadings above 0.5 except this one, 0.4, which I'd mentioned. And then evidence of discriminant validity is we had no strong cross-loadings. Another bit of evidence for discriminant validity is this factor correlation matrix. We can look and see at all these non-diagonal values and make sure they're not above 0.7, which would indicate sharing a majority of the variance. So the closest one is this factor 4 to factor 6. I'm guessing that is information acquisition and decision quality. I can go up here and check. 4 and 6, yep, those are those two. And they are highly related, but not so related that they're sharing a majority of their variance. So that's the closest one. What would I report? I would report the pattern matrix at a minimum. You may also want to report this factor correlation matrix. Okay, that is adequacy, convergent validity, discriminant validity. If we want to do reliability, you just do like I did before. Go do a Cronbach's alpha scale reliability analysis. We did it for information acquisition. Move those over. We'll do another one for decision quality, but not all decision quality items. We only have 2, 3, 4, 5, and 7. 2, 3, 4, 5, and get rid of 6 and 8. Whoops. So 2, 3, 4, 5, and 7. Throw those in there, hit OK, and report this number here, 0.901. What I like to do is just stick it at the top of my pattern matrix. So this 0.901, I would go stick it right here. That was decision quality, so I'd replace this 4 with 0.901 and then put Cronbach's alpha right over here. Okay, you want all those Cronbach's alphas to be greater than 0.7. If they're not, there's actually literature that says it can get down to 0.6, particularly if you have only a few items, 2 or 3. And that is the EFA.